Now let's talk about some of the practical considerations of insulation systems. It can result in increased losses, primarily the iron losses in the stator core or the rotor core in some instances. The shortened life may lead to warranty claims or damage to a shop's reputation, and it is important to understand and identify problems caused by the accelerated heat aging. A recent TAPI paper entitled Pulp-Coated Motors, The Effect on Motor Life, was published by several gentlemen from a major paper company and the General Electric small motor plant. TAPI, by the way, stands for the Technical Association of the Pulp and Paper Industry, if you're not familiar with that. But what they were looking at was getting back to the idea that we mentioned initially, that the normal expected life of a winding is in the 20 to 25 year range, but they were experiencing failures in a much shorter period of time, 2, 3, 5 years, where everything would indicate that under normal operating conditions the motor should go for the normal life expectancy of 23 years. So the question becomes, why is this happening, and is there anything we can do about it? Well, they took some motors and they actually ran tests. They coated the motors with pulp from the mill to block and cover the cooling passages. They partially obstructed the air intake to the fan enclosure and did various things to determine the impact on the temperature rise of the motor while performing its normal intended function. And they used a very interesting example to demonstrate the point that I'd like to share with you. They used an example of an actual scenario that you could verify. Some slides developed from some information presented in another IEEE paper entitled Mechanical Behavior of Stator End Windings, again produced by some Japanese gentlemen from Toshiba. This slide shows the typical distribution of forces on the end turn of the coil. And as you can see, it is not uniform, and because it is not uniform, it's trying to bend and distort the coil into various shapes. Below that is shown the strain distribution as would be measured on the surface of the coil when it's subjected to forces of the pattern as described above. Now, remember again that these forces are both vibratory and steady-state DC forces trying to permanently deform the coil as well as trying to make it vibrate. But by seeing that force pattern and the strain pattern, it offers some insight as to how the coil should be blocked and braced in order to minimize the vibration, in order to minimize the motion. Because if you looked at that previous pattern there and compared where you would put your blocks, if you put the block right at the point of minimum force, or a node so to speak, it is not going to reinforce the coil, and it's going to allow it to deform and vibrate pretty much as it wants to. So the location and the number of the braces or the blocks or the ties is very critical in determining and limiting the amount of vibration and displacement that coil will be subjected to. Just take a practical example and consider what we see in the next couple of slides here. Here are the end turns of an actual winding on a large machine in the 5,000 horsepower range. And note that each coil has 3 ties, 3 rows of blocks and ties, and obviously we're looking at the bore side of the coil here. And on the back side, the coils were tied to a ring, and there were 2 additional rows of blocks and ties. This was on the original winding. And the machine was rewound because of winding failures. In the new winding, the bracing was considerably different. Where there were 3 rows of blocks and ties, there is now 1 row of Dacron felt blocks. On the back side, the coils are tied to the ring, but there are no additional rows of blocks. So somebody made a conscious decision to go with a lesser degree of bracing on this winding as opposed to what was on the original equipment. Now, the original equipment had an asphalt flake mica insulation system, and this has another type of system which is not thermoplastic and is more mechanically rigid, but at the same time, the question would be, is this stiffness of this insulation system by itself sufficient to warrant the decrease in the number of blocks and ties that were used on this particular machine? Because, as you're well aware, blocking and tying and bracing is a very labor-intensive operation, which requires many man-hours in a large machine, or even a few hours in a small machine, and that can make the difference between the cost being within the limits of what one expects and being excessive. And sometimes decisions are made to compromise the blocking and bracing without a full understanding of the ramifications and the dangers that are being taken as far as courting the possibility of a premature failure of the machine. Now, it is beyond the